Now we are moving into the fourth example. In the fourth example, we started with the filtration. Fn is a sequence of sigma fields, and this is the filtration. Let x be any random variable with the random variable is integrable. Define xn is a conditional expectation of x given fn. So you are defining a sequence of random variables with the help of the conditional expectation of the random variable with the given the information up to n, or the filtration n. So suppose you want to prove the sequence of random variable or the stochastic process is a Martingale, then it has to satisfy the three conditions which we discuss in the discrete time of a Martingale property. So the first we are checking whether the random variable xn is integrable. So if you want to prove the xn is integrable, then you have to prove the expectation in absolute random variable has to be a finite. If that is finite, then the random variable is integrable. So this is same as expectation of in absolute. You can replace xn by expectation of x given fn. You can take the absolute inside the expectation, and this is nothing but it is a absolute of x, because that is a way we define, since xn be any random variable with the expectation is a finite, and you know the definition of expectation x given y is going to be expectation of x. So we are using that property. Hence expectation of x given the filtration fn is same as expectation of that random variable. So here the random variable is absolute x, and this is already proved that it is a finite, therefore this is also going to be finite value. Hence the expectation of absolute xn is finite, the random variable xn is integrable. So the first condition is verified. By the definition of conditional expectation, xn is a fn measurable. The way we have written xn is a expectation of x given fn. So this is the definition of conditional expectation. Whenever you write conditional expectation of x given fn and that exists with the xn, that means the random variable xn's are fn measurable for all n. So by the definition of conditional expectation, xn is fn measurable for all n. So the second condition also satisfied. Now we are going to verify the third condition. The expectation of xn plus 1 given fn is same as, you can replace xn plus 1 by the definition, that is expectation of xn given fn plus 1. You are replacing xn plus 1 with the conditional expectation given fn. You know the property of the filtration. The filtration property is f1 contained in f2, f2 is contained in f3, and so on. Therefore fn is contained in fn plus 1. If you have two sigma fields and one is a sub sigma field of other one, fn is a sub sigma field, fn is a sub sigma fields of fn plus 1, then the conditional expectation of conditional expectation x given fn plus 1 given fn is same as conditional expectation of x given fn. We are using the conditional expectation given sigma fields with the two sigma fields fn contained in fn plus 1. We are using the property. Hence expectation of x given fn, by the definition expectation of x given fn is nothing but xn. Therefore this is equal to xn. So left hand side we started with the expectation of xn plus 1 given fn. The right hand side we will end up xn. This is the third property of this is the third condition we have defined it in the Martingale property in discrete time. So hence all the three conditions are satisfied by the sequence of random variable xn's. Therefore, the stochastic process xn is a Martingale with respect to the filtration f. Because we have used this filtration to conclude xn is a fn measurable and find out the conditional expectation is same as xn, and the random variable xn is integrable. Hence, the stochastic process is a Martingale with respect to the filtration fn. Now we present the example which was introduced in the beginning of lecture in this model. So this is the example we have given as a motivation for the model Martingale. A player plays against an infinitely rich adversary. He stands to gain ₹1 with the probability P and lose ₹1 with the probability Q. We are defining the random variable xn, the player's cumulative gain in the first n games. What will be his fortune on the average on the next game, given that his current fortune? We are asking the measure in a conditional expectation. The game is fair if and only if this sequence of random variable xn is a Martingale. And that is possible. This sequence of random variables or this stochastic process will be a Martingale when P and Q is equal to off. That means when the game is fair, that means whether he will gain ₹1 or he lose ₹1 with the equal probability 1/2 and 1/2, then in the game is fair. Whenever the game is fair, the given stochastic process is a Martingale, and also whenever the given stochastic process is a Martingale, in that case the game will be a fair game, and that means the P and Q will be off 1/2. The conclusion is, it says that the player's expected fortune after one more game played with the knowledge of entire past and present is exactly equal to his current fortune. The conditional expectation of his one more game expected fortune given the knowledge of entire past and present, that means the filtration till time t or till time n in the discrete case, that is same as exactly equal to its current fortune. That means it is same as expected, that is same as x suffix n for a discrete case, or it is x of t for a continuous case. So whenever the game is fair, that is a P and Q is equal to off, then the given stochastic process xn is a Martingale. And the conclusion of this problem is the player's expected fortune after one more game played with the knowledge of entire past and present is exactly is important, because later we are going to say more than or less than. For that we are going to name the different. So here it is exactly equal to his current fortune.